Remember the last time at the end, I give you a formula, Fibonacci numbers formula using the golden ratio representation. I call it magic formula because nobody can guess that formula. The question is, how do you know the formula is correct? How do you know it? Right? You need to prove it. Because the formula is given, so we have it. So what we need to do is just to verify it. To verify it, we need to verify for all n. Fibonacci numbers for all n. But the n takes the value 0, 1, 2, 3, infinite many values. The question, how can you verify a formula with infinite different values? Here, we will answer that question. So we start with special cases first. First few special cases. After that, then we do the general case verification. All right. Yep. So let's start how to show that this formula is correct for all n. Starting from 0, 1, 2, and all the following n numbers, natural numbers. Phi, the golden ratio representation. Okay? Yeah. All right. Verification, the first case, it should be very easy. Right? N equals 0. Let us plug in 0 number into that formula. So phi to the 0, that's 1. 1 minus 1 over 1, that's 0. So it's trivial. So we make it. Case number 2, F1. Let us plug in n equals 1. This time we need to do some calculation. But the second term, 2 over 1 plus root 5, the denominator is a little complicated. In this situation, we do one typical operation. So we multiply numerator, denominator, something called a conjugate, right? Conjugate number. Yeah. So this one, we can multiply, after we multiply the conjugate. So what do you mean the conjugate here? Multiply 1 minus root 5. 1 minus root 5. Right? Yeah. The same thing. Yeah. So you do not change the whole fraction value. But then you do the simplification. Yeah. So the numerator here, it becomes 1 minus 5, negative 4. Numerator 2, 4, cancel out, so you have 2 at the numerator. But negative sign, you switch root 5 and 1, so you get that expression. So root 5 minus 1 equals 2. After this change, so you can see, because you have the common denominator, right? So and the numerator part of negative 1, 1 cancel out, 2 root 5, then root 5 and this root 5 cancel out, right? 2, denominator 2 cancel out, so you get this 1. So that's the same as the initial value we have here. So case 2, we also will verify. Let us verify a few more cases as a practice. All right, so case 3, let's do one more, case 3 here. But this time, phi square, much harder, right? We need to take square on that golden ratio number. Yeah. So then, the square, we have formula, right? Yeah. We have formula, we can calculate that square. Yeah. All right. So here, the conjugate thing, yeah, we already did in the case 2. So we just, use the new form by case 2. Yeah, so we can save some time here. Yeah. But we need to do some simplification. So multiply everything out, cancellation. Yeah. All right, so here, after I multiply out all the terms, then cancellation, 5, 5, 1, 1 cancel out. 2 root 5 minus negative, it becomes plus 2 root 5, right? So 4 root 5, outside root 5 cancel out. 4, denominator 4 cancel out. So we get 1. We know it's correct because 0 plus 1, that's 1. F2 equals 1. We know that easily. So here you can see we verify the first 3 Fibonacci numbers. Targeting that formula. It's correct. All right. But we cannot do this kind of verification forever, right? Yeah. So we have to stop somewhere. Yeah. Another thing is, you can see when n becomes larger and larger, the verification becomes harder and harder. Probably quickly, we cannot handle the computation. Too complicated. So we won't go too far. Okay. All right. Next, let's move another step forward. Still verification, case number 4. Actually, we do not have to do this verification, but here I just do another verification. I want to show you how to use the golden ratio property to do some algebra operations. Golden ratio property. So in this case, when n equals 3, I won't multiply everything out because that's too complicated. Okay? Yeah. Although we can handle it, but I don't want to go that direction. So I want to change a different direction. So this time, I use the golden ratio properties. All right, so let me show you how to use it to do simplification. We need to calculate this expression. But I won't plug in phi number. I want to use the golden ratio property to change the form of this expression. Here we notice the degree relatively high, degree 3. So we know the higher the degree, the harder the computation. So to make it easier, we just want to bring down the degree, lower the degree. But how to lower the degree? Golden ratio property. So what's the golden ratio property? All right. Yeah. Remember, how do we find the golden ratio? From a quadratic equation, right? Do you still remember what quadratic equation we use to find golden ratio?
x squared minus x minus 1 equals 0. Right? Yeah. So that's the starting point of the golden ratio. It means if we plug in golden ratio into this equation, the equality holds phi squared minus phi minus 1 equals 0. Must be correct.
From this equality, we can get 1 equals phi squared minus phi? We just move 1 minus 1 from left hand side to the right hand side. So 1 equals phi squared minus phi. Yeah. That's the first property, golden ratio. All right? Yeah. And we can also, we move 2 minus terms, negative terms to the right hand side. We get a phi squared equals phi plus 1. So we have these two golden ratio properties. So we can apply these two identities to simplify our golden ratio related expression. Here, let me show you how to use it. All right, yeah, so that's the, yeah, how we get that. Okay, all right, so let's start work. Phi Q. We want to bring down the degree. Phi Q too high, bring down the degree. So we split phi Q as phi times phi squared. But when you see phi squared, we can apply the second property here, right? Replace phi squared by phi plus 1. How about that? Phi plus 1. The degree is 1 lower. When you do that substitution, the degree is 1 lower. Phi times parenthesis, phi plus 1. 1 lower. So then multiply through phi squared plus phi. You see another phi squared term here. So we can replace this phi squared by phi plus 1 another time. And after we combine the terms, 2 phi plus 1. This expression, you can see the degree becomes 1. So we lower down the degree from 3 to 1. Original degree 3, here degree is 1. See? So let's leave there. Okay? Let us work on 1 over phi q. This fractional expression harder than the phi q because it's at the denominator. But we still, this time, we do the simplification. We replace the numerator 1 by phi squared minus phi, the first equality. Why we do this? Here, you can see 1 is very simple, but you replace a simple number 1 by a more complicated expression, phi squared minus phi. The reason, there is a good reason to do that. Because after this substitution, the numerator and denominator, they have common factor, so we can do cancellation. Common factor phi. After cancellation, we get a phi minus 1 over phi squared. Cancellation. Okay? We like the cancellation. Okay? We like more and more cancellation. Next time, you see 1 again, right? Another 1, minus 1, another 1. Can we apply that, the first property of golden ratio another time? Replace 1 by the whole expression phi squared minus phi.
after simplification, we get a 2 phi minus phi squared because we can do another cancellation. Common factor phi again, another round cancellation. All right. After cancellation, you can see the form is pretty simple. 2 over phi minus 1. That should be enough. That should be simple enough. Okay. After that, let's add up these two terms and see, can we find its value? All right. Phi cubed plus 1 over phi cubed. All right. After simplification, 2 times parenthesis phi plus 1 over phi. Okay? That parenthesis part actually corresponds to the F1 part. F1 we have the structure. So if you compare it with F1, so what is F1? F1, so you change n to 1 in this formula. Right? That's F1. Okay? Yeah. So if you compare, you can get this simplification. F3 equals 2 F1. Just looking at this expression, but you multiply 1 over root 5 both sides. 1 over root 5 both sides. Okay? Yeah. Then what do you get? Just F3 equals 2F1. And we know F1 is 1, 2F1 is 2. So you'll find F3 value, that is 2. And based on our recurrence relation, this 2 number is correct. Okay? Here you can see we do the verification with the golden ratio properties, 2 properties. Yeah, so here, I like you to, so when you do the computation, try to do it in a smart way. Okay? Try to do it in a smart way, so not a messy way. Not a messy way. In this first assignment, I didn't give you any questions related to the golden ratio. I will leave to the next assignment. So the second assignment, you need to do some calculation using the golden ratio properties to simplify some expressions. Okay? All right. Got it. After this, so you can see we verified another case, case number 4, but we have to stop somewhere. Because no matter how many cases you verify, you cannot say you cover all the cases, right? Because there are infinitely many cases. And nobody can verify infinitely many cases in this straightforward way. Straightforward way. But we can prove it. We can prove it. This formula is correct for all n numbers, for n non-negative integers. Always correct, without verifying all the cases. We can do that. So next, I will show you how to do that. D.2, verify Fibonacci for, why special cases again? It should be general case. Yeah, general case. general case, only one case. We treat the general case as only one case. Okay? All right, so this time, we need to apply a powerful tool here. Okay? So let me review. So you learned this in your discrete math. This is a very important tool in math. Mathematical induction. Mathematical induction. Here, so let me show you how to apply it. Mathematical induction. Okay? Yeah. All right. In mathematical induction, there are 3 steps you need to complete the whole procedure. The first step, base cases verification. We did it. We already did that part. Check the base cases. F0, F1, that's enough. You only need to check 2 base cases. But we did 4. So we did more than that. So we can pass the first step. All right. Then step 2, we call it induction step. Sorry, assumption step. Induction assumption step. We need to make induction assumption. Okay. Let me show you how to make that assumption. Assume that the formula is true for 2 less than or equal to k less than or equal to n. Okay? Here. We verified it, the 2 case, right? So we verified the 2 case already. Okay? So that n could be bigger, could be smaller. We could, because this second n is a variable. We can change its value. But its smallest value here is 2. Okay? The smallest possible n here is 2. So when we make this assumption, at least we know when n equals 2, this assumption is correct. We verify it, right? It's correct. Okay? All right. Yeah. And this assumption tells us when k falls in this range, this formula, you can assume it is correct. But this assumption, we build it on top of our step 1 verification step. So it is built on top of the step 1 verification step. So it's not an arbitrary assumption. So there is a base for it, not arbitrary assumption. Okay? Because we have our base case checking to back it. All right. That's step 2. Now the critical step. Step 3 is the most important step. Step 3. Formula is true. That means we can use this formula. Okay? But this time we use that k. The k change in that range. Any number in that range, we can use it to replace that k number. Okay? So we put there. All right. Step 3, verify. The critical step. Verify that when k equals n plus 1, the formula is also true. This step, we need to do algebra verification. Algebra. Because this time, when you see the k number, when k number equals n plus 1, it is out of this range. Out of this range. When it is out of the range, you cannot apply this assumption. So you have to use algebra operations to prove it rigorously. Then the conclusion, so you will see the conclusion will be what we need to do, what we want to have, the conclusion. Now, I will explain the conclusion after we finish the step. All right. Let's work on the last step. We do formula transformation. The recurrence relation, we can use it. Because this is from the recurrence relation. It must be true. Fn plus 1 equals Fn plus n, Fn minus 1. Directly from the recurrence relation. So it is correct. Okay? So we start from this formula. Next, then f of n, remember the induction assumption when k falls in this range between 2 and n, this time the k equals n falls in that range, so we can use this formula by our induction assumption. It is legal. We follow the rules. K is in the range, so we can apply this formula. If K is out of the range, we cannot apply it. We follow other rules. Right. The second term, Fn minus 1, you can see n minus 1 is also in that range, right? It is also in that range. Okay? Yeah, because actually, if you worry about, we can change the range to 1. How about that? Yeah, because to make n minus 1 in the range, probably we like to reduce 1. That would be better. 1 less than equal to k less than equal to n. So n minus 1 also falls into the range. Yeah. So in our induction assumption, we just change the lower bound to 1 because it's also correct. Okay? All right. Then we can apply the formula with k equals n minus 1 by induction assumption. It's also legal. Yeah. Also legal. Okay? Yeah. All right. So then only thing we need to show is this formula. This formula. Okay? Yeah. This formula. Okay? Yeah. All right. It looks a little complicated. Yeah. All right. How to show it? How to show it? Yeah. So compare the destination formula. This is the destination formula, right? This is our current expression. So we want to show our current expression just the same as the destination expression. Okay? That 1 over root 5 part is the same, we can ignore it. We only need to consider the part inside the big parenthesis. We only need to compare that part, the major part. Ignore 1 over root 5. Okay? Yeah. Then, how to compare? It looks still a little complicated, right? It looks still a little complicated. To compare, can we try to compare based on the structure, based on their structure? So when you observe each representation, you can see 2 parts. One, the integral, another fractional part. The integral part, fractional part, 2 parts. structure, the integral part, they have similar structure, right? The fractional part, they have the similar fractional structure. So can we naturally connect in this way? The fractional, the integral and integral part should be the same. The fractional and the fractional part should also be the same. So the fractional one, structural wise, it should be compatible. Okay? That's our understanding. The understanding of this problem. We understand it this way. Okay? So based on the structure, integral structure should match integral structure. Fractional structure should match the fractional structure. Okay? Yeah. That's the natural connection. Yeah. All right. Yeah. So let's work based on this. You can treat as a guess because we haven't proved it. You can treat as a guess. We want to make good guess here. All right? Yeah. So let's show the first equality. The first equality. Okay? How to show it? That's easy. We start with our second golden ratio property. Phi squared equals phi plus 1. That's our second golden ratio property. Number 2. Okay? Yeah. We know it's correct. Then let us multiply both sides by phi to the power of n minus 1. Both sides. It should also correct. Left hand side, phi to the n plus 1. Right hand side, phi to the n plus phi to the n minus 1. That's exactly our first equality. So it's correct. So we verify it. Then we have more confidence on the second equality. Although it's a little harder because this time we have more confidence. We know it must be correct. We just need to verify it carefully. Okay? Yeah. All right. Now let's verify the second equality. To verify it, so here we like to take another commonly used method in problem solving. I remember I mentioned a little bit before, that's the backward thinking. We go backward. Backward, that because this should be our destination, right? This should be our destination. That's the end. The end of the whole story. Destination. Okay? But now we go backward thinking. So we start with the end. And then moving backward. Okay? And try to get something we can handle. Then we go forward. So you can see it's a two-way. Okay? We can move both ways. All right. So the back. Moving from our destination backward, the first step we want to do, remove the common denominator. Common denominator, because we don't like the denominators. So we want to remove all the denominators. So let's multiply the common denominators, both sides. All right. After multiply the common denominator, you can see we get this new form. This new form. But this new form, still -1, power of -1, still cause some problem. We don't like this part. Power of -1. Okay? Yeah. Because we cannot see our formula clearly. Okay? We cannot see our formula clearly. So we want to remove the power of -1 structure in this formula. So how to remove it? Let us multiply both sides by -1 to the power of n minus 1. Yeah. So you need to find appropriate power of -1. Here, this is the appropriate one because the left-hand side would become 1. Yeah, because n plus 1 plus n minus 1 equals 2n. -1 to the 2n, that's 1. Right-hand side becomes phi squared minus phi. Yeah. Phi squared, the coefficient is 1, positive. And the phi, its coefficient is -1, negative. Yeah. So it becomes phi squared minus phi. But this is our first golden ratio property, right? This is our first golden ratio property. We know it's correct. We know it is correct. Okay? Now, because we get something that is correct, so we can go forward. Because every step when we do deductions, that's the two-way deduction. Okay? So we can go both ways. So after we get a correct some identity, we know it is correct, then we go forward all the way to the destination. So the destination one must be correct. Now, that's our last step verification. Last step verification. Okay? Yeah. All right. So after that, we can make our conclusion. We can make our conclusion. The whole formula is correct. The whole formula is correct. Okay? Can you get it? So why you can claim the whole formula? Whole formula means this is correct for all n. All n. Based on the mathematical induction, we can make this conclusion. All correct. But here, let me explain a little more here. Yeah, because you may not, some of you may still feel not comfortable why we can claim the formula is correct for all n. Yeah, some of you may not feel comfortable. So let me explain. Okay. All right. Let me start from the induction assumption. Our induction assumption covers this range. When k falls in the range between 1 and n inclusive, the formula is correct by induction assumption. But only in this range. Okay? All right. But our step number 3 here, so we did all the work we have done for step number 3. What's that? What do we really do at this point? What we do is we expand the range from n, we enlarge the range from n to n plus 1. Is that? Because we show for n plus 1 it's also true. So we can enlarge the range by 1, right? Yeah, we prove it. By rigorous algebra, we prove if the range covers to n, so we can enlarge it to n plus 1. Okay? That's the importance of step 3. Why I say step 3 is the critical step. Because we can enlarge the range. One more. Bigger. Okay? Alright. So one more bigger is fine. Can we enlarge another one more from n plus 1 to n plus 2. Yeah, because one more is always okay. It's always fine, right? So if we get our range covered to n plus 2, can we cover n plus 3? So we can always do it like this forever, right? So our range will cover all natural numbers. That's the reason mathematical induction is correct. Because we can always enlarge the range to cover all the numbers. That's the reason. But what do you need to prove? You only need to prove you can enlarge the range by 1. That's enough. By 1. Yeah, only by 1. This one number larger gives you the capability to cover infinite numbers. How about that? How about the power? Yeah. Why mathematical induction is so powerful? Yeah. The essence is here. The essence of mathematical induction is here. So, one number larger is good enough to cover infinite many numbers. Feel about this point. Feel about it. So you know 1 is important. Your improvement by 1 is so important. Because you can keep doing the same thing. Okay? Keep doing the same thing. Okay? So there is no limit for your range. Keep doing it. Alright? Alright, so we finished this topic. After this topic, now we have 100% confidence. The Fibonacci formula given here is true. Okay? This is the rigorous proof. Okay? Now, this is the rigorous proof. Yeah. That's why it's important. Okay? All right. Now, any question? Moon, just remind me before you leave, check your name. Attendance. All right. Next topic. Yeah. So let me do another 10 minutes. Then we move to homework. Okay. All right. Deep 3, linear recurrence relations. So this topic, we need to solve linear recurrence relations. We need to find some systematic procedure to solve this type of questions. Before we do that, here I want to solve a problem we left in the Tower of Hanoi problem. Remember? In the Tower of Hanoi problem, we derive a recurrence relation, this one, recurrence relation, but we didn't solve it, right? We didn't solve it, so we put here. In this topic, when we start, let's solve this relatively simple case, because it is very simple. So let's find the solution of this one first. Okay. Yeah. All right. Although it looks simple, but still you need to find some smart way to solve it. Because this recurrence relation, so you may feel not that easy to see the answer quickly, right? All right, so here, we need to do some important formula transformation. So here is another. So we know in math problem solving, formula transformation is very important. Okay? So here, let me show you formula transformation. How do we do right formula transformation here? Okay? All right. Yeah. Look at the structure both sides. So we need to make some good observation on the structure of our formula both sides. Left-hand side, what's the difference between left-hand side and the right-hand side? Right-hand side, there is that plus 1. Left-hand side, there's no constant term. The plus 1 is the constant term. So left-hand side, you have a constant term. The right-hand side, you do not have a constant term. That's the difference. The structure difference. We know if the structure is not closed, then the harder to solve the problem. If the structure looks similar, then it's easy to solve the problem. But how to make similar structure both sides? That's the most important thing. How to make the structure both sides look similar. Okay? So that's the consideration here. Another thing is, if we ignore the plus 1 term, is it much easier? If no constant, if for some reason, we know we cannot draw that constant term, but we just imagine. If the constant term is gone, is that very easy? Yes. Every time you just multiply by 2. Every time you move to the next C function value, you just multiply by 2. That's so easy. Unfortunately, there is that constant plus 1 term, so we cannot do that. So the reason it is harder, because there is such a constant term as the roadblock. So we want to remove this roadblock, constant term. The next question, how to remove the constant term? By formula transformation, using some smart manipulation. Very smart. Okay? Anyone can see some special smart trick to, try to take away that constant part.
C of 1. C of 1 can be replaced. 1 can be replaced with C of 1.
Yeah. All right. So here, all right. The point is, we add 1 both sides. We add 1 both sides. The right-hand side, C of n plus 1. The left-hand side, 2 C of n minus 1 plus 2, right? Plus 2. But the 2, the good thing is we have 2. It's a common factor. Can we take that 2 out? C inside parenthesis, C of n minus 1 plus 1. So we get this new form after this operation. Think about it. Yeah. The importance of this, because we make both sides have the similar structure, right? Left-hand side, C of n plus 1. Right-hand side, also C of n plus 1. Structure the same, right? Yeah. Same structure. Because they have same structure, can we introduce a new function for this expression, d function? We make it d of n equals C of n plus 1. How about that? We introduce a new function called D. Okay? D of n equals C of n plus 1. Because after we introduce this D function, the constant term is gone. Right? Yeah. The constant term is gone. The original recurrence relation becomes D of n equals 2 times this side is just a D of n minus 1. Right? Yeah. So 2 times D of n minus 1. That's the new form. And the constant term is gone. Think about it. How good it is. Okay? Yep. And remember, after we introduce this D function, we also need to update its initial value. D of 1 equals 2. Right? Update it. Initial value must be updated. Right? D of 1 equals 2. Right? Yeah. Then we know, because every time we increase the parameter by 1, we just multiply by 2. Okay? D of 1 equals 2. D of 2 equals 2 squared. Right? D of 3, every time we increase the parameter by 1, then our answer, power of 2, the exponent is increased by 1, and so on. Okay? So this tells us D of n equals 2 to the n. Power of 2. 2 to the power of n. Here. Right? But we want to get a C function, right? So let's go back to the C function equals D function minus 1. 2 to the n minus 1. How about that? So the formula for C function has been derived. C of n equals 2 to the n minus 1. So we find a solution. Yeah. So you can see the whole analysis. So we went through a lot of logical reasoning, analysis, and finally we get here. We get our final answer. Then the conclusion. Remember, this is for the problem power of Hanoi. So we need to go back to the power of Hanoi. How many disk moves do we need in order to solve the n disk power of Hanoi problem? The answer is 2 to the n minus 1. 2 to the n minus 1, the formula. Okay? Yeah. So that means where n equals 10, how many disk moves you need to make to solve the 10 disk power of Hanoi problem? 2 to the 10 minus 1, that is 1023. That many disk moves. Then, in our homework assignment 1, you have one question related to power of Hanoi problem. So in that question, you need to use this form. You need to use this form. Okay? But that question, we solve power of Hanoi problem twice. The first time, the second time. Okay? The first time, we need to make certain number of moves. The second time, we need to make certain number of moves. Then I add those two numbers together, I tell you that number, the sum of those two moves, number of moves. Then I ask you, what is the disk number for the first time? What is the disk number for the second time? That's the question. Okay? But with this formula, you can find a solution. With this formula.
Okay? You need to do some work, but you can find it. All right. Yeah. So let's move to the homework questions. If you have some question to ask, yeah, so you can raise the question. Yeah. Here, let me just bring up the, the question file. All right. Yeah. Yeah. So let me quickly bring up the question file.
I have one question.
Yeah.
What page, when you reference pages, what is that reference? Like, is there a book for it? I wasn't aware of it, but is there a book for that?
Yeah, yes. Yeah. Page, yeah, textbook. All right. Yeah. Over. Yeah. All right. Any question? Anyone? If not, yeah, we have 10 minutes. So let me explain. The question relatively hard. All right. The first one, question 21. Okay. Given a 135 element array, what is the minimum number of comparisons that you need to find an element that is among the bottom 5 in the sense of values? Bottom 5. One of the 5 lowest numbers.
And are all elements distinct or not?
Yeah, all elements distinct. Yeah, good. Yeah, all elements distinct. Yeah. Finding the minimum. Yeah, remember that. Here, connect this question to that. Finding the minimum question. Closely related. Minimum question you can treat as bottom 1. How about that? Okay? Not a bottom 5. So you change the 5 to 1. Then it becomes the finding the minimum. Okay? Now you want to find bottom 5. So the hint I want to give you here, because some students, so here, I point to the right direction. Okay. First, for finding the minimum, we know the number of comparisons we need, n minus 1. Right? N minus 1. That's the optimal solution. N minus 1. Okay? Yeah. The first thing is, if we just apply finding the minimum right here, we get an n minus 1. N minus 1, we find the minimum. Actually, we overdo the problem, right? We do more than necessary, right? Because we don't need to find the minimum. Just the bottom 5, one of the one in the bottom 5. But we do more than that. We find the bottom 1. What you need to do is bottom 5, but you get bottom 1.
the bottom one, the answer is, the bottom one answer is 134, but this is more than necessary. That means your answer should be smaller than this number. Okay? Smaller than this number, your answer. If more than that, yeah, think about it. If your answer is greater than this number, it must be false. Because we can take this solution, right? For example, your answer you give me 140. It must be false. Because we can take this 134, right? Yeah. So you only need to do better than this number, smaller than this number. Because you do not need to do that much work. Okay? Yeah. Bottom 5, just close to bottom 1. How about that? You have some room to get close to bottom 1. Think about that. Not really the bottom 1. Okay? From close to exact, still you need to do some more work, right? Now you can save that part of the work. How about that? This view. This view. Okay? So that is, the first hint. Think about it. First hint. Okay? All right. Second question.
I was going to ask a question 22.
Oh, 22.
Is everything in place except X5?
Yes. X5 is not. Oh, sorry. Oh, no. Yeah, don't make that assumption. That assumption is too much. Okay? All right. So 9 elements. X5 not in place. That's what we know. For other elements, could be in place, could be not in place. Yeah. Arbitrary. Other locations arbitrary. But this one, not in place. Okay? All right, think about that. All right, another one. Yeah. Yes. I only have the time for another question. 5 minutes. The last one I want to talk about. Question number 24. Given a 6-element array with distinct elements, say x1, x2, x through x6, it is known that x1 is not a minimum. x1 is not a minimum. That's the only thing we know. Okay? That's all we know. All right? Is it possible that one can use just 2 comparisons to find an element that is neither the maximum nor the minimum? If yes, please describe the main steps of your solution. 2. So the target is 2 comparisons. 2 comparisons. So this question, remember, related to one of our quiz questions. Our quiz question, 500 element array, can we use fewer than 8 comparisons? The answer is 3 comparisons, right? Because we can reduce to 3 elements. So the answer is 3. Now let's take that solution here. 6-element array, if we do not have this condition. So if we ignore this condition, it's not there. But we want to find one element that is neither the maximum nor the minimum. Using that solution 3, right? 3 comparison, we can find one neither maximum nor minimum. 3. But here, then we put this condition back. We have more information. Can we do better? Right? Better than 3? That's the reason our goal is to get 1 fewer comparison than that 3. Yeah. We know
condition, we can get 3 comparison solution. But now, you need to make use of this condition. Well, try to fully use this condition. This condition is very useful in a smart way, so you can reduce the number of comparisons by 1. It's non-trivial, it's pretty tricky, yeah. But for the manipulation, just a small number of elements. How hard can it be? How hard? Just a few elements, right? Yeah. It's non-trivial, but it cannot be too hard, right? It cannot be too hard. Okay? All right, yeah. So after hints for these 2, probably the hardest questions in this assignment. Yeah. So that hopefully you can, try to find some ideas. Here, you need to really do a lot of logic thinking. Really do a lot of logic thinking. Okay? Yeah. Do not expect to find some easy answer somewhere. All right. Yeah. Try. All right. That's it.